difficult to get started, but you know, do get started and stuff. Okay, so Jan pulled me up. Jan was watching the recording and he noticed that I said something like, of course you did equivalence relations in first year, and we had a bit of discussion about whether there really was a good treatment of equivalence relations in first year. Well, I'm not going to say a huge amount about it. We'll deal with that as we encounter them. I will just say, just to dispel, it's there on page 11, but just to fill you in a little bit. Okay, you're very familiar with relations in a mathematical sense. Example, integers x and y, or let's say real numbers x and y, is x greater than y. May or may not be true, depending on values of the integer, the values of the real numbers. If we have integers x and y, we might say that x divides y. May or may not be true, depending on what particular values x and y have. Okay, so these are examples of relations. They are not, well, they are statements. Okay, things that can be true or false. I was going to say not things that have a value, like a numerical value, but very often computer scientists and mathematicians do speak of these things having a value. They have a truth value, either true or false, often encoded as 0 for false, 1 for true. Okay, but relations are these things here that form statements. Okay, these in particular are examples of binary relations. Binary meaning the two inputs into relations. Of course, a very fundamental importance is the relation of equality. Okay, x is equal to y. It may or may not be true, depending on what x and y are. And equivalence relations are a special type of relation. Relations satisfying certain properties. They're technical looking and sounding properties. But before we get into discussing the properties, I just want to draw a picture. Okay, this is a set with elements. In this course, that thing, that egg-shaped thing, a load of dots in it, is going to be a group. These are going to be all the elements of the group. And that might be very complicated. There might be a lot of elements in there. There will come a time where we want to simplify our view of the group in a certain way. And the way we simplify it is by producing what's called a partition. A partition is where you take your large set of elements and you split it up into what might be called cells or into subsets in a certain way. Okay? It's like erecting a load of fences. Set, okay? Very simple, intuitive idea. Okay? Every element of the set, the large set, is contained in one and only one field, cell, whatever. Okay? There's no elements trapped on the border around. Okay? There's no element that is simultaneously in two different ones. And there's no overlap between the cells or the subsets. Okay? So that thing is called a partition. And equivalence relations and partitions of sets go hand in hand. Whenever you've got a partition of a set, you can form an equivalence relation by saying that all the elements within a cell are all related to each other. So these are all related to each other. These are not related to any of the other ones, only the ones in their own cell. And these ones are all related to each other, not to any of the other ones, only the members of their own cell, and so on and so on. Okay? So that's a very quick, intuitive, easy idea. Everyone's familiar with that idea, so to speak. Just like you can divide all the citizens of the UK, residents of the UK, say you can divide them up into the counties that they live in. Greater Manchester, whatever counties, a bit less obvious. Greater Manchester, Lancashire, there's historic counties and industrial counties. But in Ireland, it's very clear, they're very prominent parts of Ireland. related to this. Everybody knows what county. I don't even know what county are we in. Cheshire.
Lancashire.
Not Cheshire.
Yeah, Lancashire, but now
Now
Manchester
it's
has
great,
this.
yes. So there's a lot of, if you're in Ireland, you know what county you're in. Yeah, okay. Anyway, and so what's an equivalence relation? An equivalence relation is, okay, it has three properties. Reflexive. Now, it's traditional when you're speaking about equivalence relations in the general, it's traditional to use a tilde to represent it. One of the ASCII characters on the keyboard, tilde. So you think of the tilde as something like greater than or divides or equals, but it's a non-specific, just some kind of relation. Okay? So there are three properties that it has. So it has to be reflexive. Let's call this large set X. We've got these little elements, little X inside it. For every X in the set, X is related to itself. That is true of the relationship of equality. It's also true of the relationship divides. Every integer does divide itself. Of course, it's not true of the relation strictly greater than. Okay? No real number is strictly greater than itself. Okay? So the greater than on the real numbers is not reflexive. Symmetric property says for every pair of elements in the set, if X happens to be related to Y, then it is also true that Y is related to X. Remember that with binary relations, there is a notion, it's an ordered pair of elements. There's a first element and a second element relate in this relation. And it potentially makes a difference which way around they go. Not for equality, yes for divides, because a small number can divide a large number, but not vice versa. And it's also for greater than. If X is strictly greater than Y, it's never the case that Y is strictly greater than X.
Is that why you use the right arrow? Because it's not, as you did yesterday.
This one?
This one, yeah. When you say so like backwards, you can say that if Y is equivalent to X, you could also say X.
Yeah, we could.
Y.
Yeah, so actually I could put a double-sided arrow on that. So X being equivalent to, X being related to Y is equivalent to Y being related to X. Okay. The relationship always goes both ways, so it's called symmetric. And then the last one is transitive. Transitive refers to a state of affairs between three elements. And it refers to this situation where you have X related to Y, and that same Y related to something else. It must also then be the case that the X is related to Z as well. Okay? So this says the relation tilde is transitive. The relation travels through intermediates. So Y here, you could call it an intermediate. It's just the way it's presented there, an intermediate between X and Z. If X is related to Y and Y is related to Z, then X is related to Z. Of these three example relations we have here, only equals is an equivalence relation. The other two aren't for various reasons. Strictly greater than fails on symmetry and reflexivity. Divides in the number theory integer sense fails on symmetry. 2 divides 4, but 4 does not divide 2, and so on. Although divides is transitive, strictly greater than is transitive as well. If X is bigger than Y, and Y in turn is bigger than Z, it is always true that the X is bigger than Z, if those are real numbers. Yeah. So, and there's a kind of theorem connecting these two, equivalence relations and partitions, saying that whenever you've got an equivalence relation on a set, if you look at all the elements, if you pick a particular element and look at all the other elements that are related to it, that will form a certain cell or subset. And then keep doing that. Keep picking an element that hasn't been used yet, gather together all the elements that are equivalent to it. You keep going in that process, you'll construct a partition of the set. So the equivalence relation gives you a partition and vice versa. If you start off with a partition of the set, I didn't list, so there are technical conditions associated to our partition, but pretty much just encapsulates the idea of fencing off the interior of a set, such that everything is one side of the fence. You know? If you've got a partition, that induces an equivalence relation on the set. Okay. Okay. Right. Okay. Well,
Don't you remember the total that you made? Didn't we do this and remember?
Yes, it's
yeah,
just like-
some debate about maybe we should.
Laura, don't you remember it looked like a really six turtle? You turned it into a turtle, you gave it legs and a little head. Do you not remember?
Is it drawing it?
I draw on all my notes.
So here's a real example we might look at. So you all probably recognize this statement. The rationals are fractions of integers, ratios of integers. So what is a rational number? It's something formed by a fraction of integers. For instance, 3/7, 2/4. Okay. But if you say something like that, there's already a technical problem, you see, because we want to say that 3/7 and 15/35. Really, we want to say that they're the same rational number, don't we? Divide below by 5. Yeah. So the ratio is the same. The rational number represented by those fractions is the same.
Is it just been scaled up?
Just been scaled up using the normal multiply top and bottom by number. But you see, if you really want to be very formal and very careful, those are different fractions. Okay. They're different ingredients. This is a 3 and a 7 arranged. This is a 15 and a 35 arranged. So the fractions are different. So the set of fractions isn't really somehow the set of rational numbers, okay? But we can partition the set of fractions to obtain the rational numbers, okay? So we don't necessarily want to say that the rationals are all the fractions, because really, strictly speaking, to be really pedantic about it, these are different fractions, okay? Representing different processes. To divide the 3 into 7 parts is different to divide 15 into 35 parts. Okay? You get the same number of parts, or it's the same ratio. So so the question is, if you've got two fractions, what is the relation? What is the correct relation? And it's actually an equivalence relation. That induces a partition of fractions to give you the set of rationals. Meaning that once you partition the whole set of fractions, each cell will be a different rational number. So in terms of the A, B, and C, D, without talking about fractions and rational numbers, can we quote the relation just purely in terms of integers? Well, we can do that. So we will say that A over B is equivalent to C over D. Because really I object to saying it's equal to, because in a strict pedantic sense, this fraction is different to that fraction. But we'll say that we'll regard them as equivalent if and only if B times C is equal to A times D. And there you see the relation is expressed without any reference to rational numbers, just with reference to the integers and properties of the integers, multiplication of the integers. And that exactly encodes the situations where the two fractions represent the same rational number. So 15/35 and 3/7 would be gathered together here in this cell, together, of course, with the infinite amount of other representations of that same rational number. And 2/4 and a half would be gathered in another cell, together with the other infinite number of representations of that rational. Okay. So this is an example of an equivalence relation on the set of fractions, on the set of formal fractions. And when you impose this equivalence relation, you get a partition of the formal set of fractions, which will give you the rational numbers. This is a quick, relevant, meaningful example. And you need to exclude 0 in the denominator position as well. Okay. Okay. Now we'll encounter equivalence relations and partitions again, because there will be situations where we'll be looking at a complicated group and we want to simplify them. We're going to partition its elements mathematically. Okay, so we will encounter that idea again, and we'll be concerned with those 3 properties: reflexivity, symmetry, and transitivity. But we'll deal with them once again. Okay. Okay. Any questions? Okay. So that was the material in chapter 1. Preliminaries on sets, mappings, and their equivalence relations. Looking at chapter 2, everything in it we covered last year in the number 2. Okay. And the particular importance of that for studying groups, some of the material we're going to be looking at is classifying the structures, classifying the structure and possibilities for the different types of groups that there are. And at its simplest, this concerns itself with looking at the size of the groups and looking at the sizes of the possible subgroups that there are within a larger group. So the size of a group, of a finite group, of course, is going to be measured by integers, the number of elements in it. So, and the relation of divisibility is going to play a crucial role. So this chapter 2, if you look at the kind of things it revises, it looks at induction, mathematical induction, which is the property that characterizes the integers. And it looks at the Euclidean algorithm, greatest common divisors, prime numbers, and so on. Okay? But all of that material, to page 28, will be very familiar to you from the number 3 course. So, if you don't mind, I think we'll just jump in and start doing some exercises with I don't want to lecture the second year number theory course again. So we're going to stay active a bit. So let's have a look at some induction proofs. Let's look at question 2. On page 29. The proof technique of induction is going to be used in the group theory course. Page 29, exercise 2.3, question 2. So let's go through an example of induction, stressing the important features of the proof by induction technique. Okay, this formula is dealing with the sum of cubes, going from 1 up to n. This is 1 cubed, it's 2 cubed, etc., all the way as far as n cubed. The sum of cubes has a very nice formula, which is quadratic in nature, and is apparently given by that. N squared times the square of n plus 1 over 4. It's not blindingly obvious by any means. Okay? You should expect it to be quadratic, because summation, remember, is kind of like integration. So if you're adding up a load of cubes, your mind should link that with the integration of the cubic function, which you know gives you a quadratic order 4 expression. So it's not exactly just simply n to the power of 4, but it is something that's order 4 in n, and that's to be expected. Okay. So how can you prove such a thing? Well, this is clearly, or this is a classic case of calling out for proof by induction. Because it's really an infinite number of statements indexed by n. So n is equal to 1, this is a certain statement, n is equal to 2 is another statement, n equals 3 is another statement. The one for n equals 1 is like trivially simple. Yeah, we just got 1 cubed on the left-hand side. It should be equal to 1 on the right-hand side. So, you know, it's trivial to just observe it's true for n equals 1, and then hopefully we can perform the inductive step to show that the truth for one value of the index implies the truth of the next value. Or from the truth of the statement for one value of the index, one can quite nicely, easily derive the truth of the next version of the statement. So the base case here should be n equals 1. There shouldn't really be anything to prove here. It should just be a simple observation. So if you add up j cubed for every value of j between 1 and 1, well, there's only one option. One value of j is just 1 cubed, that's definitely equal to 1. Is this equal to, so n is 1, 1 squared by 1 plus 1 all squared over 4. Oh, yeah, because here you've got 2 squared over 4, which is just 4 over 4, which is just 1. Okay? So that's a 1 squared. So just by observation, it's true. So the base case is true. Now what we're trying to do is to prove the inductive step. Okay? That the truth of the formula for one value of the index implies the truth of the formula for the next one. So that's an implication we want to prove, so we should prove it directly. So just assume the left-hand side and try and derive the right answer. By that I mean that we assume that the sum from j equals 1 to k, j cubed, is equal to the appropriate thing, k squared, square root of k plus 1 all over 4, for some value of k greater than or equal to the base case 1. We're not being specific about the k, just say suppose it's true for one such value of k. And that's a valid assumption to make because we've just proved the base case. So there is at least, it's not a silly assumption to make because we know it's true in one of these cases. Okay, so now we just kind of loosen our viewpoint a little and just say, we'll assume it's true for a generic k. Without proving the base case, you wouldn't, there would be a question mark over this approach. Because what if this formula was never true for such a k? Then you shouldn't really assume that, unless you're going to do proof by contradiction or something. If you want to do a positive constructive argument and you're going to make an assumption, you better be sure that you're allowed to make such an assumption. We're allowed to assume this for a generic k greater than or equal to 1 because it is true for at least one such k. Okay, and now we attempt to derive from this assumption. So I'm trying to spell things out very clearly here. Derive from this assumption the formula for k plus 1. And we'll try and prove it directly. So on the left-hand side, we've got the sum of all the cubes from 1 to k plus 1. Yeah, I think it's okay. And we want to build a chain. Remember, often we can approach these things that we just want to bridge the gap. So we know where we're trying to go. If at all possible, when you're constructing these arguments, if you know what the destination is going to be, you may as well put it down the page or make it visible in front of you. So the formula for k plus 1 looks like this. That's what the required formula is when k is replaced with k plus 1. So that's where we're trying to get to. Hopefully I've left enough room. So how can we
Start with the sum from 1 to k.
Yeah.
And then add on the extra term.
Yeah. So break down this big summation. Just take the last term off of it when j is k plus 1 and leave the rest packaged up together, which will be this here. And then we can do straight substitution. So this is certainly the sum from j equals 1 to j cubed, just going up as far as k. That summation on its own. And then we'll separate the very last term, which is when j is k plus 1. So you've got j cubed, k plus 1 cubed. Now we've got a cubic term in k. Okay, what we want is goes up to order 4, but so this looks like it could make a valid contribution to that. Yeah. And this we can just replace using our assumption. K squared, k plus 1 all squared, 4. K plus 1 cubed. So this is manipulating, this is just manipulating the sum. This is from the assumption. I should have left myself a little bit of extra room. I mean, you could just, audaciously, confidently declare that these two are equal. If they are equal, you surely have to be very convinced.
Just me, in coming back to these notes in 7 months' time.
Yeah.
And I'll just go, how did I just assume
Yeah.
that?
How did I declare that? Yeah, you're right. I mean, it's not immediately obvious, but you can start to see, like, you need a k plus 1 squared. There's a k plus 1 squared here, and in there is a k plus 1 squared. And you need a quarter. There's a quarter. So start to pull those things out. So let's pull out k plus 1 all squared over a quarter. So that appears here. And what's left behind in the first term? Well, it's just k squared. And what's left behind here? Well, there's one of the k plus 1s left behind. We took out k plus 1 squared, but there was k plus 1 cubed.
Yeah.
So there's k plus 1 left behind, but we also took out a quarter. So we should leave behind a multiple of 4 to compensate for taking a quarter out. So this should be 4 times k plus 4. Or 4 times k plus 1. See, I took this 4 out of there, because it was there, just pull it out. And there's no 4 there to pull out, but of course there is, because you can imagine a 4 over 4.
Yeah, yeah.
I just pull out the 4 at the bottom, so these will sit behind the 4 at the numerator. Yeah. And 4 times k plus 1, so it's 4k plus 4. And k squared plus 4k plus 4 is indeed the square of k plus 2. So that is clear now. Factoring. So I think now if you did come back to those notes in a few weeks' time, I think you would be convinced by that. But the point is, what we've done, it's a bit colliding on top of each other there. But if you look at that right-hand side and the left-hand side we started off with, that is the required formula when n is k plus 1, isn't it? Where did that come? How did we arrive at that? Well, we did some algebraic manipulation, but crucially, we used the assumption. We used the assumption we just made. That's the crucial. So we didn't prove this from nothing. We didn't prove that this is true. We proved that it's true, assuming the previous one is true. That's the crucial flavor of induction. Okay. We proved the required result, assuming it was true for the previous case. And then you invoke the principle of induction. The fact that you've established the base case, you prove the inductive step. The principle of induction then tells us that this result is going to be true for all positive integer values of the index n. So we attempt to derive from this assumption the formula for n equals k plus 1. This completes the derivation. Just trying to package the whole thing up. This completes the derivation. This derived derivation, that finishes that derivation. And so by induction, principle of induction, and formula is true. Formula is true for all values of the n greater than b. Okay, and it's kind of understood in the context that these are integer values of n. Right. Is that okay? clarification we might offer on that? And the great thing about this book is the amount of exercise. Look, we go up to page 31. Thousands and thousands of exercises. Plenty of food there to digest and work with. So, lots of those induction things are of that kind of similar ilk, with certain kind of summation formulae. And might be good to look at one that isn't, one's a little bit different. We go to question 11. That's an inequality. So inequalities that are indexed by the integers are kind of good candidates for induction as well. So we might look at question 11. What does this say? Question 11 says if x is a non-negative real number. So let x be an element of the reals, and it's non-negative, so the x is greater than or equal to 0, I should say. Show that one plus x to the power n, subtract 1 from it, that is greater than or equal to n times x. So if we were to add a positive increment or non-negative increment to x to 1, raise it to the power n, look how much that advances us from 1, the difference with 1, we'll find that we've at least gone this value of the index n times the increment x. We could put quite a geometric interpretation on this in terms of steps along the number line, if you like, or advancements along the number line. But really, this is an infinite set of inequalities indexed by n. Okay. We should understand that n is positive integers. Does it give a starting value? So n equals 0, 1, 2. Okay. So n is an element of the integers. N is greater than or equal to 0. Okay. So again, a good candidate for induction. Base case shouldn't be like that hard to prove. We just want to carefully make sure we're looking at the correct version of the formula, and it's probably just going to be an observation. But of course, here the base case is n equals 0, because we're required to prove this for every value starting from 0. Base case is n equals 0. So what are we looking at there? We're looking at 1 plus x to the power 0 minus 1. Well, if x is bigger than or equal to 0, then this is certainly a non-zero real number. Raised to the power 0, by definition, is 1.
Put minus 1.
Put minus 1,
Yeah.
which equals
0.
0.
Which is
And what relationship?
by an x, and n is 0. 0 times x is 0.
Yeah. So it's actually equal to, but we won't write equals, we'll write, let's write greater than or equal to. I mean, it is equals, but yeah. I mean, that looks a bit weird, but you should be writing equals there. But just simply for the sake of, to show that the formula, the inequality is satisfied, you may as well just quote it as greater than or equals. So really the base case is just an observation, not really proving such. So the base case is true. That sound good? So again, just like in the previous one, look at the structure of scaffolding. Base case, make the assumption, a little note to yourself about what has to be done next, do the thing, and then just, it's like invoking the principle at the end. So we've done the base case, we should make the assumption. So we assume that 1 plus x, if we were to raise it to the power k and subtract 1, this would be greater than or equal to k times x for some k greater than or equal to 0. beware of what base case you're using, whether it's 0 or 1 or something else. So now we need to, from this, we'll derive the inequality for n equals k plus 1. You know, the first thing to try is just to try and establish it directly. Start with the left-hand side, try and do it to the right-hand side, or vice versa. And if you stumble in that, if you get stuck in that, then you might start to try and think about doing proof by contradiction or somehow coming at it in a different way. But our first attempt should be to establish it directly. So the left-hand side of that inequality would look like this. So what am I going to do with that? Split it up. Yeah. Split that power up. Yeah. So inspired by what we did with the summation, instead now we're going to factorize this. Factor off the power k. And then we need the extra factor, 1 plus x. And then you still got the minus 1. And I have to say that this is equal to this, of course. But there it is. This is the expression appearing in our assumption. So I can bring it in. I don't quite have the minus 1. Well, let's just put the minus 1 over the other side. So I can replace 1 plus x to the power k. I can replace that with 1 plus k times x. Still got 1 plus x here. I've still got minus 1. But I've replaced the 1 plus x to the power k with something smaller. So this is now greater than 2. So that's just manipulation. This is from the assumption. I'm trying to relate this to k plus 1 times x. K plus 1 times x. Yeah, well, we will see that if we, I think we should multiply out this bracket. You get 1 plus kx plus x plus kx squared. And you still got this minus 1. The ones cancel, you got kx plus x, so that would go to k plus 1x, which is what we wanted on the right hand side. Yeah. Agreed? K plus 1 times x for the next value of the inequality, and we've still got this kx squared. So what do we do from here? What do you say? I haven't got my right-hand side yet, so I'm looking for on the right-hand side. So I started with the left-hand side. There I was trying to get the right-hand side, which was k plus 1 times x, but I've got this thing there irritating me. So what do we do? Should we get rid of it in a way, or?
Can we divide through by kx?
Well, if you start dividing through by
We just expanded that bracket to k plus 1x. Wouldn't we have another kx? We don't want to get rid of that, do we?
if we divide this through, I mean, then you are introducing a denominator in. See, this looks lovely and clean here because this is exactly what I want over there, isn't it?
You divide through by x.
Divide through by x, well then I'll just be left with a kx, then I'll have an x, then I'll lose the k plus 1 times x if I divide through by x. And I'll either have I'll either have to multiply the left-hand side by x. No, I'll have to either divide the left-hand side by x to compensate, or keep this x in the denominator there. So I want to do as little as possible to this, because I don't want to destroy this nice thing, because that's exactly what I want. But you can remember, see, we're not building a chain of equations here, necessarily, because we're trying to establish an inequality. So we don't just have, so we pass through a few equations, we also pass through an inequality. As long as we keep going in an inequality in the right direction, the result will still be intact. So really, I can just let it go, dismiss it, just get rid of it. Okay, it's kx squared. Well, x squared is certainly a non-negative number, no matter what x is. It happens that x is non-negative itself. K squared is certainly a non-negative bit. K, what are the possible values for k? K squared is equal to 0. So this bit that's hanging around, which I don't want, is certainly non-negative. Probably big. I can just get rid of it. And just say that this is greater than here. So from beginning to end, we do get, well, actually we get something slightly stronger than we need, I think. Well, no, sorry, strictly speaking, sorry. 0 is a possible value for x, so I shouldn't say strictly greater than, because in the special case for x is 0, then this is only equal to this, because they're both 0. Yeah. But from beginning to end here, I've got the left-hand side is bigger than or equal to the right-hand side, which is what we want. Okay. So this completes the derivation. This derivation I claimed I would do. Okay, are you have a problem seeing that?
Yeah. Getting rid of the k.
So-
Why do we not care about the k?
Well, I mean, you might care about it, but it's not you're not required to care. This is the result we're trying to prove for every value of k, or it was quoted with an error before. I mean, there's lots of stuff missing, you know, comparing the left-hand side to the right-hand side, there's loads of detail missing. Because all this is saying is that the left-hand side is bigger than the right-hand side. So it's by no means the full story about these two things. Yeah. So although this looks like extra information, and indeed it is extra information.
If it's bigger than that, it's going to be bigger.
Yeah.
That's all I need.
Okay. So yeah, if you want to retain as much information as possible, you would retain the fact that there's a kx squared error term, or you know, an extra bit.
So the equal, like it's got an inequality and then two equal signs. Can they be inequalities?
Well, yeah, you see, yeah, okay. Then what you need to do now is think about the overall transitive nature of these relations. So I said this is the same as that, and it's the same as, no, I said this is the same as that. That is no less than that. It's bigger than or equal to that.
Because
That-
substituted in
Yeah,
inequality.
because yeah, exactly. So this greater than or equals sign is that greater than or equals. We then developed that with an equality. We just did an algebra, we just rewrote that by multiplying out the brackets. We did it again to cancel the ones and do another bit of factorization there. And then we did another inequality, but this inequality comes from forgetting this, because this is a non-negative bit. Because k is bigger than or equal to 0, x is bigger than or equal to 0.
If it's greater than all of that, then it must be greater than a bit.
Yeah. Yeah.
I don't know how to write that.
Well, I think it crucially depends on the fact that we were certain that this term is non-negative. Because if this was in fact a negative number, you wouldn't be able to go forgetting about it and claim that this is bigger than that. Okay? Because in order to get rid of the negative number, you'd have to add loads to the expression. So in which case this would be less than that. So it crucially depends. So this greater than or equal to comes about because kx squared is non-negative. So the justification for this is since kx squared is greater than or equal to. So that completes the derivation. So by induction, the inequality holds for all n within reach of 0. Okay. So that's a couple of examples of good induction proofs. The submission problems we've asked you. Oh, no. The submission problems we've asked you to work on are questions 10 and 17. So question 10, I hope you look, it looks quite approachable in that way. Summation formula. This is the pattern in the denominator, n times n plus 1. So you're summing 1 over j times j plus 1 from 1, j equals 1 up to j equals n. And the claim is that this is equal to n over n plus 1. So that's question 10. Question 17, when you look at your reading notes, that's the other submission problem. This combines a bit more of the number theory elements, because this is dealing with the Fibonacci sequence. Fibonacci numbers is this sequence here, and there's a number of facts that you're asked to prove about. Each Fibonacci number is less than 2 to the n. Fn is less than 2 to the n. The product of two, well, not exactly adjacent ones, is equal to the square of the middle one, so minus 1, and then the index n. Wait. A nice formula for Fn. And a nice limit expression for the ratio. This is the so-called, isn't this the golden ratio? Golden mean thing? Yeah. And proves that Fn and Fn plus 1 are relatively prime. I think but look, many of these are calling out for a proof by induction. This is a thing indexed by n. This is a thing indexed by n.
That last one isn't right.
This is a thing indexed by n. Well, maybe. Again, it's indexed by n. Fn and Fn plus 1 are relatively prime, co-prime.
Relatively prime.
So there's a base case here, and then maybe you can use induction.
But there is even numbers within the Fibonacci sequence. There's an 8.
Yeah, but this is only saying, it's not saying all of the Fibonacci's are co-prime to one another, it's just saying adjacent ones are co-prime.
So 8 and then 13.
Yeah.
Right.
Which are co-prime. So you never have an even one beside another even.
Oh, yeah. Within those set of numbers.
And although there's multiples of 3 and 21, but they're not beside each other.
Yeah.
Because it's talking about Fn and Fn plus 1.
Yeah. Right. That somewhat helps.
Okay.